Okay, sorry everyone. We had some technical issues that we tried to resolve. Now, I think we can continue now. So I was trying to explain the determination. How do we determine order of reaction? And like I said, to be able to determine order of reaction, the first thing is, okay, what are you even trying to find out? And we already said that order of reaction is the factor by which rate increases when you increase concentration. Remember, when you're talking about order, it's about responsiveness of rate to concentration changes. So when you're looking for order of reaction, what you're looking for is by what factor does rate change if you change concentration. Essentially, that's what you're looking for. And the best way to be able to see that is to vary concentration and look at how it affects rate. But again, there are times when you have two reactants. You have reactant A and B. If you have reactant A and B, then you want to know how does A affect this reaction independent of B, and how does B affect this reaction independent of A. So what you do is you keep the concentration of one constant while you vary the concentration of the second one. So for example, if you're dealing with A plus B to give you C, you want to know what is the order of A, what is the order of B? Or what is the order of reaction with respect to A, what is the order of reaction with respect to B? Then that means if you want to find out the order of reaction with respect to A, you fix the concentration of B while you vary the concentration of A and see what happens to rate. Then you now want to find out what happens to B. Then that means you fix the concentration of A and vary the concentration of B. Then that will tell you, when you vary the concentration of B, what happens to the rate of reaction. Now, the relationship between the change in concentration and the corresponding change in rate, that is what tells you the order of reaction. And how does this even communicate the order of reaction? Look at the first rate law there, where you have rate is equal to K multiplied by reactant. In this situation, you're saying that the reactant is raised to the power of 1. This is the first order reaction, because if it was raised to anything different from 1, if it was raised to 0, then we won't see the reactant there. We won't see that reactant there at all, because it will be equal to 1. If it was raised to 2, of course, 2 will be written there. But the fact that you have rate is equal to K multiplied by reactant, that is saying that this is the first order reaction, because that reaction, or the concentration of that reactant, is raised to the power of 1. Now, what does this mean when you say the order of reaction is 1? What it means is that when you increase the concentration by a factor of 2, then the rate will also increase by a factor of 2. Say, for example, if you have a concentration of 1 molar and your rate was 2 mole per dm cube per second, now you now increase the concentration to 2 from 1. That means you double the concentration. For a first order reaction, the rate will also double. Whatever you do to concentration will happen to rate for a first order of reaction. You double concentration, rate doubles. You triple concentration, rate triples. You quadruple concentration, rate also quadruples. That is a first order reaction. For a second order reaction, whatever happens, whatever you do to rate, whatever you do to concentration, you see it in twofold in the rate of reaction. If you double the concentration, rate will come in fourfold. If you triple the concentration, rate will come in ninefold. Sorry, I think I need to quickly correct myself. I said that whatever you do to concentration, you get double. No. Whatever you do to concentration, you get a square of that in rate. Not double, you get a square of that in rate. meaning that if you double concentration, you will get 2, because double means 2, then you get 2 raised to power 2, because we're talking about second order reaction. The power is the order. And that means we're going to get 2 raised to power 2. That means when you double concentration, rate will quadruple. When you triple concentration, you'll have your rate in 9-fold. When you quadruple concentration, that means you're going to have your rate in 16-fold. If you increase your concentration by 6-fold, that means you're going to have your rate in 6 raised to power 2, because the second order reaction, you're going to have your rate in 36-fold. That is the meaning of rate of reaction. And that is the relationship, or that is how the relationship between change in concentration and change in rate determines the rate of reaction. And that is why order of reaction is the relationship between change in concentration and change in rate. If you increase or if you change your rate, by what fold does your concentration change? That is the order of reaction. And that is what we just demonstrated on this slide. We already said for a zero order reaction, it doesn't matter what you do to concentration, your rate will remain the same, because it does not. That means the concentration of that reactant does not affect the rate of reaction. Now, let's look at this example here. Now, you have, remember what I said, that if you have 2 reactants, you want to determine the order of reaction. For A, in this case, you're talking about A plus 2B to give you C. You want to determine the order of reaction with respect to A first. Then you also want to determine the order of reaction with respect to B. Now, you want to keep, say you want to determine for A, or according to this table, the first thing that they dealt with was to determine the order with respect to B. What happens on this table? You'll see that for experiment 1 and 2, the initial concentration of A was kept constant. Why they doubled the initial concentration of B from 1 to 2 times 10 raised to the power minus 2 molar. Now, in such a situation, and you'll see that A concentration is constant, B concentration got doubled. Now, the question is, okay, what now happens to rate? The rate moved from 1.5 times 10 raised to the power minus 6 molar per second to 3 times 10 raised to the power minus 6 molar per second. That means that when you double the concentration of B, rate of reaction also doubled. And remember, the concentration of A was kept constant. And we're using the initial rate method here. Remember, when I was explaining instantaneous rate, remember we spoke about average rate and instantaneous rate. We said instantaneous rate is rate of reaction at a particular point or at a particular time. So initial rate of reaction is another form of instantaneous rate, or is instantaneous rate at 0 time. Immediately you commence your reaction, you want to measure the rate at that particular point in time, at time 0. That is initial rate of reaction. So it's just a form of instantaneous rate of reaction. And the reason why they're using the initial rate here, if you want to know the rate at concentration of 1, then it means you have to measure that rate immediately the reaction commences. If you wait too long, you're no longer measuring that rate at that concentration again, because the concentration would have changed dramatically or drastically in such a way that whatever rate you're measuring is not going to be the rate of concentration of 1 again. And that's why they are using the initial rate method is used in this case. So now for the second part, now you look at experiment 3 and experiment 1. You'll see that for experiment 3 and experiment 1, the concentration of B was kept constant, while concentration of A was varied. Now, concentration of A was varied from 1 to 2. It was also doubled, just like we doubled A, just like we doubled B originally. Concentration of A doubled now, while B was kept constant. Now look at what happens. You need to look at the experiment. You need to look at the rate of reaction. We're looking at experiment 1 and 3 now. So look at the rate of reaction for experiment 1 and 3. The rate of reaction changed from 1.5 times 10 raised to the power minus 6 to 6.0 times 10 raised to the power minus 6 molar per second. You double concentration, rate of reaction quadruple. You double concentration, rate of reaction quadruple. Now, what happened? In this situation, what that means is that when you double the concentration and the rate quadruple, that is a second order reaction. Or the reaction is second order with respect to A. While in the case of B, you double concentration, rate doubled. The rate of the order of reaction is 1 with respect to B. But of course, according to this question, I think I'm jumping the gun, but I was just trying to use this to demonstrate what I explained earlier. But again, if we look at the question says, oh, sorry, something is also wrong with this slide. Write the rate expression for the reaction. That's the A part. Then the B part says calculate the rate constant for the reaction. Now, the solution, of course, you're trying to write a rate expression for this reaction, A plus 2B to give you C. That means the rate expression is going to be R is equal to K multiplied by concentration of A raised to power X. That X is the order of reaction with respect to with respect to A, and concentration of B raised to power Y. That Y is the order of reaction with respect to B. Now, you can't complete a rate equation or a rate expression without the experiment, because now we don't know the order of reaction. We only wrote X and Y. Now, the whole idea of this conversation is now from this data, how do we now find out our X? How do we find out our Y? Now, and of course, like I said, you're going to be comparing what happens to concentration. In this case now, you're comparing concentration, and the comparison is to know by what factor did you increase concentration. So when you compare the original concentration and the second concentration, it's obvious that the concentration was doubled. Then, by what factor did the rate also increase? That means you're also comparing the two rates. That means the rate, what is this now? Comparing 1 and 2. Okay, sorry, 1.5. This is 1.5. So sorry, there's a mistake here. This should be 1.5, not 1.0. So that should be 1.5. So so the rate changed also by a factor of 2. Concentration changed by a factor of 2. Rate also changed by a factor of 2. Now, the question is, from that now, what is the order of reaction? What is the order of reaction? Now, the rate ratio, and that is the formula now to use this this inspection method. Is the rate ratio is equal to the concentration ratio raised to the order, raised to the power of order. The rate ratio is equal to the concentration ratio raised to the power of order of reaction. In this case now, we're talking Y, and that's why the rate ratio is equal to 2, the concentration is equal to 2, then we'll raise it to the power of or the order of reaction, which is Y. And now in this case, our Y is going to be 1, meaning that the order with respect to B is 1. Now, you want to, so that means the reaction is first order with respect to B. Now, it's the same thing now again. To evaluate X, you do the same thing. You also compare experiment 1 and 3, because you also double the experiment 1 and 3. And that comparison also tells you that you double concentration for experiment 1 and 3. And what happened to the rate of reaction? The rate of reaction also quadrupled for experiment 1 and 3. Now, how do you now determine your X from this information? You determine your X, your concentration ratio is going to be equal to rate to ratio, your rate ratio is going to be equal to concentration ratio raised to the power of the order of reaction. In this case, it's going to be 4 is equal to 2 raised to power X, and our X is going to be 2, meaning the order with respect to A is equal to 2. Now you have your complete rate equation. K is equal to A raised to power 2 multiplied by B. Or the rate is equal to K multiplied by the concentration of A raised to power 2 multiplied by concentration of B raised to power 1. This is a complete order of reaction for that equation. Now, but again, the question says calculate calculate the rate constant for the reaction. Calculate the rate constant. Remember, we were talking about the significance. I think that was, I'm not sure whether that was the first class or the second class. We were saying that you cannot use rate to characterize a reaction or to compare reaction because rate changes with concentration. That you can use rate constant to characterize reaction because it doesn't matter what you do to concentration, your rate constant is what is called a constant. A constant. So in spite of these varieties of concentrations that you see here, your rate constant for all this must be the same. It doesn't matter what reaction you're choosing. You can choose experiment 1. The rate constant you are going to get should be the same thing as if you're using experiment 2. Should be the same thing if you're using experiment 3. Remember, we already have a rate equation now. We have a complete rate equation. These are complete rate equation. You can substitute any of those concentrations here, and you should get the same rate. The same rate and concentration pair into this equation, and you will get the same rate constant. It doesn't matter which one you're using, as long as all your information are coming from the same experiment. If you want to use experiment 1, or you can take concentration from from experiment 1 and go and take your rate from experiment 2. No. You want to determine rate constant, you must use the same experiment. So if you use experiment 1, whatever you're going to get should be the same as if you're using experiment 2. It should be the same as if you're using experiment 3. So now, in this case, now I think we're using experiment to calculate the rate constant. Substitute any of these 3 sets of data into the rate law. I'm trying to find out which one are we using now. I think we're using one. Okay, hold on. I want to see which experiment. Oh, I think experiment 1. Experiment 1. So experiment 1 is used there. So because the concentration is 1 times 10 to the power minus 2 for A and B for experiment 1. Why the rate is 1.5 times 10 to the power 10 times 10 to the power minus 6. So and you get 1.5 molar raised to the power minus 2 per second. Now, you can use any of these experiments. You can try it on your own. You are going to get the same. You're going to get the same thing. Now, this is one very good method and very straightforward method of determining order of reaction with respect to individual reactants. And of course, you can determine whether the reaction is first order, second order, third order, zero order from that. Now, but there's also something called integrated rate for various orders of reaction, either for 1, either for 2. Now, more often than not, what you do with integrated rate is if you're given a set of data, or maybe I should start by saying, in this situation, you're comparing rate, your data actually has rate and concentration data. You're given rate and concentration data. But there are times when what you have is going to be concentration and time data. Concentration and time data. And what you want to do is you want to determine the order of reaction from concentration time data, not concentration rate data. What we have there is concentration rate data. Of course, you can always do rate from concentration time data, but there are times when you just want to use that concentration time data to show or to check where the order of reaction. You don't want to go through all this. You just want to say, okay, we have concentration, we have time data. You want to see, is the reaction first order, is the second order, is the third order? That is what you use integrated rate equation for. We don't want to go through the derivation of the integrated rate equation, but like I said, it is for concentration time data. What we dealt with was concentration rate data. Now, for concentration time data, what you want to do is you just want to check if, okay, somebody just gave you a set of data, you have concentration, you have your time, and check what is the order of reaction. Or show that the order of reaction is first order, or show if it's second order, show if it is third order, or you're working in the lab, you just want to see. You ran an experiment and you were monitoring the concentration of your reactant as it is changing with time. You had your table. at time 0, this is the concentration. 10 seconds, this is the concentration. 15 seconds, this is the concentration. 20 seconds, this is the concentration. Then at the end of the day, the question is, okay, what order of reaction is this? Then these are the equations that you can actually use to check. And how do you use this equation? You plot a graph with the equation. You plot a graph with this equation. If you get a straight line, and if you look at this table now, if you look at the table, for the integrated rate equation, this integrated rate equation, they came from our differential rate equation. They came from the differential rate equation that we kind of like went through, but we don't want to go through the derivation of the integrated rate law. We just want you to see those integrated rate equation and know how, or have an idea what they do and how you apply them. Now, if you now have that data, you want to check, is the reaction zero order? You use this equation. That is the first one for zero order reaction, where you have concentration of T is equal to concentration of, concentration of A at time T, which is the final concentration of A, is equal to initial concentration of A minus rate constant multiplied by T. Now, how do you use that equation to determine whether that reaction is zero order? You plot a graph of concentration at every time T against time. Then if it gives you a straight line, you know that that reaction is a zero order reaction. If it's a zero, that is a zero order reaction, and it's going to give you a slope of negative T. If you want to check if the order is 1, then that's going to be ln AT, which is the concentration at any time T, is equal to ln A naught, which is the original concentration, minus KT. How do you use that? You plot ln T against time. That should give you a straight line also with a slope of minus T. With a slope of minus K. The same thing with second order reaction. Reciprocal of the concentration of the reactant at any time T is equal to the reciprocal of the original concentration plus KT. How do you use that to check if the reaction is second order? You plot the concentration of, you plot the reciprocal of the concentration of AT against time. Then the slope of that should give you plus K. And remember, the K here is the rate constant. We don't want to go to third order reaction. We just want to stop. But of course, they're on the slide so that you can actually see, them there. But of course, for this one, I think we're just much more interested in zero order, first order, and second order reaction. Now, this is an example of what I was talking about. The hydrolysis of ethyl nitrobenzoate by aqueous sodium hydroxide was followed at 25 degrees Celsius by titration of sodium hydroxide against standard acid at different stages in the reaction. From the given data, show that this reaction is second order. Now, if you look at this, the concentration of the acid is directly proportional, because they're saying that you have hydrolysis of ethyl nitrobenzoate using sodium hydroxide, but you were following that by titrating sodium hydroxide against standard acid, meaning that the more acid you're using, the less acid you're using, the more of the sodium hydroxide you have consumed, because you have ethyl nitrobenzoate, you also have sodium hydroxide. Both of them are reacting together. And the way through which you monitor that monitor that reaction, remember we said you can monitor either the reactant or the product. You can monitor not the reactant. But in this case, they monitor sodium hydroxide. They monitor the change in the concentration of sodium hydroxide. And how did they monitor the change in the concentration of sodium hydroxide? Remember, the concentration of sodium hydroxide will decrease as the reaction progresses. Now, what they were now doing was titrating the sodium hydroxide at regular interval to see what was left. Remember, the higher the concentration of sodium hydroxide, the higher will be the volume of acid required to neutralize that sodium hydroxide. And that is why And because sodium hydroxide is decreasing as the reaction progresses, that's why the volume also decreases on this table. As time progresses, the volume of acid decreases because you have less and less sodium hydroxide in that reaction mixture. Therefore, you can, this can now be equated, or you can now assume, you can now use this concentration, because originally what it's saying is that at time 0, before the reaction commences at all, we used 10 molar. Now, if you use 10 molar before the reaction commences at all, you're saying that that 10 molar is indirectly telling you the original concentration of its volume. But the volume used there is directly proportional to the concentration. So you use 10. After 5 seconds, you use 9.3. So you can say that at the end of it, that means we have consumed 0.7 mole equivalent of sodium hydroxide. Sodium hydroxide. Then at 140 is going to be 10 minus 9 that you have consumed. That is the rationale behind this. And that is why, if you now look at this reaction, remember that what we said, if you look at the equation for second order, it is the reciprocal of concentration at any time t. Concentration at any time t. Now, to be able to determine your concentration at any time t here, you're going to be subtracting your original concentration, your final concentration from your original concentration. And that is why you are having your A0, A0 minus okay, hold on. Okay, yeah, that's correct. So now, if you now look at, because so your AT, what will your AT be from 0 to 95? Your AT from 0 to 95 will be 10 minus 9.3. Will be 10 minus 9.3. From 0 to 140 is going to be 10 minus 9. From 0 to 222 seconds is going to be 10 minus 8.5. From 0 to 334 is going to be 10 minus 7.9. That's how you do that. And that is what you actually have here. So the whole idea here is that for every set of this data, your rate constant has to be the same. If we say that the fact that I said that if you plot a graph of the reciprocal of the concentration of A at any time t against time, you're going to get a straight line. And the slope of that straight line is going to be your rate constant. What that means is that the rate constant for every set of data on that table is the same. So you can do this through two methods. You can either plot a graph where you get a straight line, and that will tell you that, oh, this reaction is second order. Or you can do it the way we did it here, where all we did was use every point on this data from here, from 0 to 95, from 0 to 140, from 0 to 222, from 0 to 334, to calculate the rate constant. And your rate constant for every set of data must be approximately the same, because it's the same thing as getting a straight line with the slope equal to k. So if you now do that for all the set of data here, you get almost the same thing, 7.92 times 10 to the power minus 2, 7.93 times 10 to the power, and so on. You get something very, very that are approximately the same. It's the same thing as saying that what you have is a straight line. And you can see that you have 0.7 as your AT in one situation. Okay, and so on. And 1.5, that is where they're subtracting this 10 minus 9.3, 10 minus 9, 10 minus 8.5. Now, there's also the half-life. There's also the half-life of the reaction. Because you can see that we have half-life expression here also. But the most important thing is, what does it even mean to talk about half-life? The half-life of a reaction is the time required for the concentration of a reactant to drop to half of its initial value. It is what it says, half-life. You're starting with 10 molar. How long does it take for the concentration to get to 5 molar? You're starting with 3 molar. How does it take for the concentration to get to 1.5 molar? The half-life of a reaction, which is denoted by T subscript half, is the time required for the concentration of a reactant to drop to 1/2 of its initial value. Now, but of course, the half-life is also coming from the rate equation anyway. The half-life came from the rate equation. We're not going through the detail of that. The only thing you just need to do to be able to get your half-life is because during half-life, remember, we said half-life is the time required for your original concentration to turn to, for your concentration to turn to half of the original concentration. Now, if you're starting from A0, that means at half-life, your AT is going to be A0 divided by 2. At half-life, because that is how you get all this half-life. In your integrated rate equation, you substitute for A0, A divided by, you substitute for AT, A0 divided by 2. That means you're going to be having, instead of it, you're not going to be having any AT in that equation again. You're going to be having A0 so that you can actually get your half-life in terms of the original concentration, if it is possible. And if you do that for the first one, that's why you have A0 divided by 2K. That's for zero order reaction. Because for zero order reaction, that is going to be A0 divided by 2 is equal to A0 minus KT. For zero order reaction, that will give you A0 divided by 2K. Because you are going to be making the T in that equation the subject of the formula. So immediately that T in that equation becomes T half, your AT becomes A0 divided by 2 in all the equation. And if you do that, you realize that you get the half-life. And it's actually very simple for the zero order. That's what you get. You want to do the same thing for the first order. That AT becomes A0 divided by 2. You get the same thing as what you have as those expressions. That is how we arrive at those half-life. Now, the next thing we want to talk about is it's actually called the chemical dynamics anyway, which is the collision theory of a reaction. Now, according to this theory, chemical reaction takes place only by collision between the reacting molecules. So for reaction to take place, if you are having a reaction between reaction A plus B to give you C, you're only going to have C if, one, those molecules are colliding, A and B are colliding with each other. But that is not enough, because the fact that they are colliding does not mean that will lead to a reaction. And that's why you can see that we're saying that not all collisions are effective. Only a small fraction of collision produce a reaction. And the two main conditions for a collision between reacting molecules to be productive are the colliding molecule must possess sufficient kinetic energy to cause a reaction. And the collision, the colliding molecule must also collide with proper orientation. So collision is not enough. For reactions to take place, there must be collision, but collision is not enough. For you to have a reaction, the collision must happen with sufficient kinetic energy and proper orientation. Those are the two conditions that must be fulfilled before a collision can become effective. Now, why is this? Because why is it that not all collision? Why are we talking about some threshold kinetic energy that must be achieved before you can actually say that a collision is effective? Because activation energy is the minimum energy necessary to cause a reaction between colliding molecules. Because when you're talking about reactant and molecule, there's something called the energy barrier between the two. Reactant and product, there's always an energy barrier. So if you do not break this energy barrier, reactants cannot transform to product. And that energy barrier is what is referred to as the activation energy. So the colliding molecule must be able to achieve at the minimum this activation energy. And it is only molecules that collide with kinetic energy greater than this minimum activation energy that are able to get over that barrier and react. I'll take that again. Between reactants and product, there is an energy barrier. Reactants, that's why they stay reactants. That's why they don't just, by just looking at them, they don't transform to product. They stay reactant and they stay there until you do something to them or until something happens to them. Because there is an energy barrier that prevents them from transformation to that thing you refer to as product. Now, to be able to get across that energy barrier or to be able to break down that energy barrier or to be able to transcend that energy barrier, this molecule must collide, and they need to be able to collide with, at the minimum, kinetic energy that is equal to that energy barrier. That is when they can form product. But any collision that takes place with energy lower than this energy barrier, they are unproductive. They are not going to lead to a product. The molecules simply bounce off each other. Then that is in terms of the minimum kinetic energy. Now, the reactant molecule must also collide with favorable orientation. That's what we're talking about, the orientation. The correct orientation is that which ensures direct contact between atoms involved in the breaking and forming of bond. Because two atoms that need to interact with each other. If the molecules are reacting with an orientation where two atoms that are supposed to be interacting with each other are not getting in contact with each other, you're not going to have a reaction. Even if you have the energy, but those two atoms that are supposed to be exchanging with each other or reacting with each other, if they're not touching each other, then there's not going to be a reaction. And that's why orientation is also important. That is collision. That is a little summary of what we refer to as collision theory. But then again, there's also something that I also want to say, because this collision theory, we're not just mentioning it. It is also very relevant to the idea of what we mentioned when we're talking about elementary reaction and complex reactions. Because I remember that one of those things we talk about is that why are majority of reactions, why are they complex? Why is it that most reactions are complex reactions and they are not elementary? It is because of this collision theory. Because for you to have a one-step reaction, it means that all the atoms or all the molecules that you have in that one step, they are colliding with each other at once, and they are giving you a product. Because there must be collision, and they're giving you a product. But it is easy for you to have such collision if you only have two molecules. So a bimolecular reaction can easily do an elementary reaction because it's just two molecules. They collide with each other. They're just two. But when you have three molecules, maybe that's also possible, but less so compared to a bimolecular reaction. A molecular reaction, three molecules, yeah, the three can still collide so much. And we're talking about the three of them colliding at the same time. It's not impossible, but it's less likely compared to when you have two molecules. So now let's even say now that's possible. Now when you have four molecules, is it possible for the four molecules or the four to collide at the same time? Now that is very, very unlikely. You are either going to have two colliding at the same time, they form whatever, that one now collide with another one. And that is why you have your reaction taking place in stages. Because when you have the molecularity of your reaction is very high, it becomes impossible for you to have simultaneous collision among all the molecules at the same time to have a single step reaction. And that is why we end up with complex reactions, because those reactions, they collide with each other in stages. Maybe two collide first, they form whatever they want to form, then now have to collide with another one or with another two. That will be the second stage of your reaction. That is why most reactions are not elementary, they are complex reactions, because the molecularity of most reactions are too high to have them as elementary reaction. And so don't just look at this like they're just sitting on that there's a relationship between this and our conversation. on elementary reaction, complex reactions, and order of reaction. Now, the reaction velocity. Okay, I think it's already 10. Okay, how many slides do we have left? Okay, we only have 3 slides. Okay, we'll find a way to deal with our 3 slides that is left. But if there are questions, please, you need to, because I always want to attend to questions before we leave. So we still have 3 slides left, but we'll find a way to do with 3 slides. Any questions, please? I don't want us to just leave without I'm sorry, I took all my 1 hour. I was actually hoping I was going to stop to give you 10 minutes to ask questions. But please, if you still want to ask questions. Raise up your, let me see your hand if you want to ask questions so that I can unmute you or ask you to unmute. Any question? Oh, okay. Adeyinka Olanrewaju. I think you unmute yourself. Okay. Now you can speak. What's going on? I can't hear you. Hello.
Good morning, sir.
Morning.
Sir, I wanted to ask, the formulas we had to learn and the graphs for the first and second order, is it the whole table or just the first,
No, no, no,
second, and zero order?
no. 0, first, and second order. You have third order. But I just wanted you to know that, of course, it's not restricted to those ones. We have more, but 0, first, and second.
Okay, sir. Thank you, sir.
All right. Another question? Any other question? All right. So I want to assume that there are no questions. So enjoy the rest of your classes for the day. Good morning.